Hello everyone, we are going to show the tutorial of the Fragro. The Fragro server contains two working modes. One is the direct grow mode, and the other is a virtual synthesis mode. In the direct grow mode, the users can replace the hydrogen atom of an input compound or replace the substructure of the input compound with any fragment directly without considering its synthesizability while in the virtual synthesis mode. The fragment is attached to the input compound by considering the chemical reaction with the functional group and the building blocks in the database. And also, the Fragro server can design ligands by performing a one-step retrosynthesis of the input compound and replacing one of the reagents with building blocks in the database. Go to a web server and have some fun. This is the web address of the Fragro server. After entering that, we need to upload a protein file to a protein pool and a ligand file to a ligand pool. First, we can prepare the protein file and the ligand file by splitting an X-ray co-crystal structure of the protein-ligand complex, or we can prepare the input files by molecular docking or some other simulation methods. We need to make sure that both the protein file and ligand file are well prepared before uploading into a Fragro server. That means the hydrogen atoms and other issues that need to be well treated with the protein and ligand file. I'm going to upload the protein file and the ligand file. Okay, after uploading, we can see that this shows the protein and ligand complex in the three-dimensional structure shows in this place. And then we can select the protein and the ligand to conduct a job. And also we need to select the growing mode. In this example, we are going to use the first one. We are going to grow a molecule through direct grow by replacing a hydrogen atom. After selecting these three items, we can click Submit. This is the second step of the Fragro. In this page, we need to select a growing vector. If we click one of them, we can see that hydrogen atom as we are going to replace. And this is highlighted in this tutorial. I'm going to grow at this point. After the selection, we can click Submit. On the third page, we can set specific protein sizes that we want to form interaction with. By default, there are several sizes that are selective. In this example, we want to form the interaction with the donor. We need to deselect as all other sites. Just leave this one selected. After the submission, we go to a fourth step. In the fourth step, we can set several parameters to constrain the fragment space. There are several items we can constrain. For example, the physical-chemical property of the ligand and heteroatom of the ligand, and ring composition and functional group. This shows some constraint for the physical-chemical property. We want to set the number of the heavy atoms. We want the size of the fragment to be less than 14 atoms. You can see it's less than 14. And that's some information about heteroatoms. I want the number of heteroatoms to be less than 2. Also, you can set some other parameters. For example, you can set the nitrogen atom number on your fragment. The fourth one is the ring composition. In this example, I would just want to set some simple set. The number of the rings to be less than 2. And for the fifth catalog, it is the functional group. If you don't like some specific function, for example, if we don't need carboxylic acids, we can set the number of aliphatic carboxylic acids to 0 and aromatic carboxylic acids also to be 0. And if we want some specific group, we can set it. For example, I want the number of amides to be greater than 1. Okay. This is a fragment source. We are running the FragRow DirectRow mode. We can set a fragment source by default. We are using fragment cut from Campbell. Also, we can say others, for example, cut from Shure Campbell or cut from PubChem. And this tutorial is going to set it. We just use the default. The last one is some other parameter to control the job. If you want to optimize the ligand with SMINA, you can set this option to 1. I'm not going to set it in this example. After our selection, we can go back and click Submit. This is the result page. We can go over these output ligand designed by FragRow one by one. Also, we can click the 3D view to see the protein-ligand interaction of the design of the ligand. Okay. And also, we can download the specific compound we are interested in. For example, if we are interested in this one, we can click download. Also, we can send the ligand to the ligand pool. We can make a second run design of this ligand. And also we can download all of these results directly by clicking here. If we are not satisfied with the ligand designed by Fragro, we can go back to the fourth step or the third step and reset these constraints and make a second run or third run. Let's go back to step 1 and run another working mode. We are going to run the second working mode. The second working mode is direct row by replacing the substructure. Also, we are going to upload another protein file from the disk and upload the ligand file. Now we need to deselect the previous protein and ligand and show our new ligand and protein. We can see the protein and ligand in there. Now we need to select the protein we just uploaded as the ligand, and also the working mode we are going to use direct row by replacing the substructure. Everything is good, and then we can submit it. In the second step, we can select specific substructure we want to replace. In this test, we are going to replace this substructure by clicking here. Then the substructure that's going to be replaced is highlighted. We can see it here, and then we can submit it. In the third step, we are going to set a protein site we want to fulfill. This site is a hydrogen acceptor that forms the hydrogen bond with the substructure we are going to replace. So it is default selected. We're not going to change this. We just select this one and click submit. In the fourth step, we are going to customize our fragment constraint. And these are constraints we used in the previous job running. We need to clear all of them and set others. In this test, we just use an easy constraint of hydrogen atoms number. That has to be less than 2, and others we are not going to constrain. Okay, after selection we can submit. Okay, this is a result page. We can check and click one of them to see the superposition of the ligand designed by Fragro and the original fragment. We can check whether they are good or not. If we don't want to see the original ligand in the 3D visual place, we can deselect them so they will disappear and a new ligand will be displayed in the 3D working space. Okay, you can also download all of them and review the ligand by other computations with us. If you are not satisfied with these ligands, you can also go back to the fourth step and modify the constraints. Okay, let's go back to step 1 and run another job using the virtual synthesis mode action with a reactive group on the input compound. First, upload the protein file and upload the ligand file. We can deselect the previous protein selectively. We are going to use a new protein we just uploaded. And use a third one, virtual synthesis action with a reactive group. And after selection, we can click Submit. On the second step, the web shows us potential growing vector that can conduct a comparison with building blocks in our database. We are going to grow in this vector, so we select here and click Submit. In the third step, we are going to select protein site that we want to form an interaction with a ligand. We are going to select this one. This is an ASP amino acid that has a receptor. And after selection, we can click Submit. And in the fourth step, we can customize the constraint. First, we clear previous sets. And because we are running a virtual synthesis job on this test, we need to first select the chemical reaction type. We are going to use Suzuki's reaction. And I leave everything as blank. And please submit it here. Okay, we get a result page. This time we didn't get as many results as previous tests. They are only about 2 pages, and that's partly because they are limited to the building block that can conduct the Stucky reaction. So we are going to try another technique that might enhance the likelihoods of finding relevant fragments. That is the shake growth factor technique. I am going to take a brief description of the shake growth vector function in the frag growth server. In reality, both protein and ligand are flexible. And this is a picture showing the ligand in the protein, and we can find that the growing vectors in the ligand could have a various position and various directions. But in our calculation, we usually use one static structure. We want to imitate the ligand flexibility in the binding pocket. So we created several copies of the original growing vector. And shake a tiny degree and generate several participated copies of the original growing vector. And we can also use these participated growing vectors to search fragments. This technique can help us to find relevant fragments. Okay, let's go back to the workplace. We're going back to the fourth step, and there's a parameter to open this functionality. In other parameter, we can shake the growth factor degree by default. This degree is set to 0. That's to set by default program, and we are not shake the growth vectors. If we select 8, this means we are going to shake the vectors by a degree of 8. Then the coupling reaction will still use Suzuki. For others, we are not going to change, so that we can submit again. Okay, the result is out. This time we get 6 pages of results, which is to see the shake factor can help us to enhance the possibility of finding fragments. Okay, we are going to run another job with this running model virtual synthesis one-step retro synthesis replacing. Because we have run several examples, there are many files in the ligand pool and protein pool. Sometimes will be really annoying. So we can reload the server and select the protein file here and then the ligand file. And after selection, we can submit. This time, we are going to use a one-step Jordan-Borman-Amide retrosynthesis reaction route and replace this part. This time, we are going to select this protein site. Then click Submit. This time, we need to select the reaction type but there is only one. And if we don't choose, that's also okay because there's only one reaction. Okay, the result is printed. And one of the features of the frag world is that users can explore the fragment space in a timely manner. The users can run several rounds of frag world job iteratively to get fragments that meet well with their project's requirements. Initially, users can run a less constrained fragment job and review the structures. And then we can go back to step 4 or step 3 and reset these constraints to narrow down the search space and rerun the job. And you can take this process several times and repeat this process until you can get a satisfactory solution. Okay, thank you. Have fun.